Hi everyone. In this video we're going to look at the rotational and vibrational spectrum of diatomic molecules. So on the slide here I'm showing two different electronic states. This would correspond to, for example, in the hydrogen atom when you have n equals 1, n equals 2. So amongst them, so let's look at this ground state electronic level. Amongst these you have different vibrational levels from the vibration, and then for even smaller energy levels you have the rotational, and here's a blow up of the rotational energy levels. So what we want to do is find out what would a spectrum look like from a diatomic molecule, and specifically we're going to look at the absorption spectrum, and then we would want to know what information can we get from that. So that's what we're going to do in this video. Okay, so before we get started talking about the vibrational energy levels, I want to remind you about the rotational energy levels. And specifically, what I want to talk about is what happens when you get a change. For example, we found that the rotational energy goes as L times L plus 1 h squared over 2 times the moment of inertia of the diatomic molecule, where L can be 0, 1, 2, so forth. So L's our angular momentum number. So what we found is a change in the rotational energy as you go from example L to L plus 1. We ended up with this. And a change in rotational energy, if you went down in L, so you went from L to L minus 1, we got this. And we can cancel those out if we want. Okay, so that's just to remind you about rotational energy of the diatomic molecule. Now let's think about vibrational energy. So what can we expect for vibration? So here's a representation of our electronic potential as a function of the separation of the two atoms of our diatomic molecule. So vibrational and rotational energies are a lot smaller than electronic transitions, which are on the order of EVs. And in fact, the only way you can see the vibrational spectrum is to stop rotation somehow of your molecule, because your molecule is going to rotate before it vibrates. And to do that, one way to do that is have your molecules in a liquid so that the interactions between adjacent molecules inhibit rotation. But let's talk about what we expect for vibration. So around the equilibrium point, realize that the potential well here looks like like it has a quadratic term. So matter of fact, if I were going to expand the potential energy, let's say about the equilibrium point in a Taylor expansion, I'd have a constant V naught plus another constant times R minus R naught to the first power plus another constant R minus R naught to the second power over 2 factorial plus R minus R naught cubed over 3 factorial plus and so forth. Now, we're going to neglect, since we're assuming we're not far from equilibrium, neglect the third order and higher terms. And the second one, the second term here, the linear term, can be 0 too, will be 0. Why? Because what is that constant? That constant is our derivative with respect to r evaluated at r naught. But that has 0 here at the bottom. So this term is also 0. So what you're left with is this quadratic term. So we can write this is approximately plus some constant. Okay. Well, we know that when we have a potential like this and we have a quantum system, we already know what the energies are. We've done that, the quantum oscillator. So the energy, which now we'll say is the vibrational energy. Now, again, this is only good when we're close to the equilibrium point. Okay? We're going to say it looks like this. This was our formula for the quantum oscillator energy, where the frequency is 1 over 2 pi square root of our first constant. So we kind of think of this oscillator as our two atoms attached by a spring with some force constant over the mass, which is the reduced mass. So the vibrational energies are on the order of 0.1 electron volts. So I will also mention for different electronic states, you have a different, we call this the fundamental frequency. Maybe I'll call it F naught. Okay. So, for example, here might be your ground state. And this is the representation of the electronic state. So this is the ground state. And you have different vibrational levels in there. And in this case, since it's the ground state, we'll call it F naught equals 1 over 2 pi square root of a force constant K naught over mu. And then there might be a different electronic state up here. This is a first excited state. And it will have its own. Now, these energy levels are not necessarily, they don't necessarily obey the quantum oscillator. As you get farther from the equilibrium point, they don't. But let's say for the first excited state, this fundamental frequency is 1 over square root of 2 pi K1, a different force constant. Okay. And then the rotational energy levels are buried in here. They're even smaller. Now let's look at spectra, and specifically let's look at the absorption spectra. So we're going to send light in to hit our molecule. And we want to see what would he expect what wavelengths to be absorbed. Okay. So we have selection rules, just like we did for atoms. And our selection rules are going to be that L has to change by plus or minus 1, and del nu has to change by plus or minus 1, the quantum number for the oscillation, for the vibration. So let's look at what happens when V equals 0 goes to 1. Okay? So the change in vibrational energy is going to be nu, let's just call it nu to nu plus 1. So the final state is nu plus 1 plus 1/2. Instead of nu there, HF minus nu plus 1/2, parentheses, HF, final minus the initial, and you can see the difference is going to be just HF. So when we get a change of delta nu plus or minus 1, we're going to get a change plus or minus HF. Okay. So for absorption, we're going to go up. And we've already looked at rotation, so what we're going to have now is change in vibration and rotational energy when nu goes to plus 1 and let's say L goes to L plus 1, we get HF plus 2L plus 1 H bar squared over 2 times the moment of inertia. Okay. And what happens if we go the other way for L? So the vibration has to be, because we're going to absorb, we're assuming we're going from nu to nu plus 1. And let's say we have L to L minus 1. That change in energy is going to be HF plus 2L H bar squared over 2I center of mass. Oh, I'm sorry, I think I need the negative sign here, right? Yeah. Okay. So, what do we expect to see? So let's say this is energy this way. And let's mark where HF is. So when we get an absorption, the change in energy is HF plus, let's say we go from, let's look at some specific cases here. Let's look at the rotational part. When we go from L equals 0 to L is 1. So we're going to increase, so that's this one here. What do we get for the change in rotational energy? We get, and by the way, you start with the L that's in here is what the L you started with. So we get H bar squared over I center of mass. And let's look if we go the other way, rotational, we go from now, when we use this formula down here, you can't start with L equals 0 because L is 0, 1, 2, and if you need a change of L going down, you can't start at 0 and go negative, so you can start at 1 and go to 0. So let's go L is 1 to L equals 0. So we put in here the L is 1, and we get, again, H bar squared over I center of mass. So our change in energy is HF plus H bar squared I center of mass. At that energy, we're going to see the energy of a photon can get absorbed, R HF minus h squared over I center of mass. So that would be this one. So this is hf plus h bar squared I center of mass. And this one is hf minus h bar squared I center of mass. And then if we went from L equals 1 to L equals 2, up here we go, it turns out it'd be 2 h bar squared I center mass. And if we went from L equals, instead of here we're going 1 to 0, if we went 2 to 1, so this is L equals 1 to 0, here's L equals 0 to 1, L equals 1 to 2, and if we went from L equals 2 to 1, we get 2, this distance here in energy would be 2 h bar squared over I center of mass. So these, you get these equally spaced absorption lines. It doesn't look equally spaced, but it's supposed to be. Okay? Now let's look at what a real spectrum looks like. Okay, so here's a spectrum from your book. This is HCl, hydrogen chloride. So first of all, it looks a lot like what I just showed you. You have these equally spaced, it looks like, absorption lines. So this would be the L equals 1 to L equals 0, L equals 2 to 1, L equals 3 to 1. Now the reason why you see two peaks here is because there's two isotopes of HCl. One has a slightly different chlorine atom than the other, chlorine isotope. So it makes the mass just a little different. So you get these two peaks, one from the main isotope and one from the next isotope. And the reason these are not all equally at the same height, so this is the amount of absorption you get, is because it's more probable that you're going to have molecules with low angular momentum than with a higher angular momentum, so that drops off like that. So right here in the center would be HF. So if you wanted to get your force constant, to model your diatomic molecule, you would use this. So matter of fact, let's use this data and let's try to find out what we can find out about the hydrogen chloride molecule. Okay, so just for a rough approximation, I want to try to find the center here. This is 860, this is 880, 870. So I'm going to say this peak is about 872, and this is times 10 to the 13, and it's in hertz. If I move this over, maybe you can see that. It's in hertz. So this is frequency, this is not energy here, it's just F. Okay, so F, our fundamental frequency here for the vibration for this electronic state, is right in the center. So 8.6, 8.72, I'm going to say the middle is about 8.67 times 10 to the 13 hertz. We're also going to need maybe the change in energies between these. So again, that's going to be h bar squared over I center of mass. So I'm going to need to try to estimate that too. Except for this is frequency on the bottom. Okay. So I'll come back to this in a minute. So we have our fundamental frequency, I said, was about 8.67 times 10 to the 13 hertz. And that's equal, since F is 1 over 2 pi, square root of k over mu. So we need mu for the reduced mass for our hydrogen chloride. Hydrogen mass is 1 atomic mass unit. For chlorine, it's about 35.5. So you get a mu is 0.973 is what I get when I put that in there. If I convert that to kilograms, it's 1.62 times 10 to the negative 27 kilograms, and that's what I'm going to want because I want to use SI units. Okay, so now I stick in, I'm going to solve for K, right? So K is 2 pi times the frequency squared times mu. It's going to be my force constant when I solve up there for K. So I stick in my values, I get 1.62 times 10 to the negative 27 kilograms times 2 pi times 8, let's put the square brackets there, times the 8.67 times 10 to the 13 hertz. And I square that, and when I put this in my calculator, I get 481 newtons per meter. So that's our approximate force constant for our model of our diatomic molecule. And we can use that if we want to know vibrational, the different vibrational frequencies around the equilibrium point. Okay, what else? Maybe we can, oh, by the way, if you look up experimental values for this, you get about 480. Okay, let's see if we can find R naught. So let's find R naught equilibrium distance. So first we're going to use the fact that I center mass for this is the reduced mass R naught squared. Okay, it's the moment of inertia of a single particle R naught from the pivot point. So what else do we know? We know that the change in the rotational energy is equal to h bar squared over. So we need that from our picture. Let's go back to our plot of the absorption spectrum. Now, what I'm going to do, because this looks like this, first of all, this is only frequency, not energy down here, and it looks like it's going to be kind of hard for me to get the difference between these different rotational energies. By the way, you'll notice, so these are supposed to be equally spaced, and they look pretty equally spaced over here, but they start to get closer together. Over here, obviously, it doesn't look the same spacing as over on the right-hand side. The reason of this is because the moment of inertia of this thing is not really constant. As you rotate different angular momentum values, the separation increases between the atoms. So these are not really, these are fairly equally spaced on this side and fairly equally spaced for the first ones on this side. What I'm going to do to try to get the moment of inertia is I'm going to look from the center, which we said was about 8.67, over to, we said this was 8.72. So what I should have is HF plus h bar squared I center of mass should be the total energy of that first line. If I divide everything by let's see, by frequency, or I'll just write this as that should be equal to h times what did we say, 8.72 times 10 to the 13 hertz, and we said this was 8.67 times 10 to the 13 hertz. So let me solve for I center of mass. So I'm going to get h bar squared over I center of mass equals h times 8.72 minus 8.67 times 10 to the 13 hertz. So I center of mass equals h bar squared over h times 8.72 minus 8.67 times 10 to the 13 hertz equals, I'm sticking that in my calculator, I get around to three significant figures, 3.35 times 10 to the negative 47. And that would be then kilograms meters squared. All right. Now using that, mu times r naught, our equilibrium distance, squared is equal to I center mass. So we get r naught is the square root of 3.35 times 10 to the negative 47 kilograms meters squared over 1.62 times 10 to the negative 27 kilograms. I stick this in my calculator and I get, I'm just going to now go to two significant figures, 1.4 times 10 to the negative 10 meters. So in your book, table 9.8 suggests I center mass for HCl is 1.3 times 10 to the negative 10 meters. So we got pretty close with our rough estimate there. So that's the kind of information you can get from that absorption spectrum of a diatomic molecule. We can get its moment of inertia, its equilibrium distance, its fundamental frequency of vibration. So a lot of information there. Okay, so that's going to do it for our rotation and vibration. I'm going to talk a little bit in the next video about lasers, and then we're going to move on.